So I just recorded all of this, but forgot to have my microphone on. So let's go again. Last week in theoretical physics, I learned continuity. What is continuity? Well, first we can talk about what isn't continuous. So let's begin with a simple function. F of x, that just means function. It just means something. It's like y equals something, blah, blah, is equal to x minus 2 over x minus 2. If you do simple algebra, that equals 1. So when we plot this, it equals 1. Boop, boop. Oh, actually, it connects. I don't like how it connects there. Boop. Ah, stop connecting. I need to show something. There we go. And now let's zoom in. Okay, so f of x equals x minus 2 over x minus 2. So this is equal to 1. But at a specific point, when x equals 2, what the? Something's acting up. Put this. What? Okay, that's acting up. Put this into your calculator and put 2 minus 2 over 2 minus 2, and you'll get 0 over 0 in your calculator, which is undefined. So this point, undefined. It ain't nice. This is called a hole. We also have something called a jump discontinuity. Discontinuity just means not continuity, not continuous. A jump, let's draw it first. Droop, droop. Oh, sweet. This is x equal, no, not f. This is not x, just 2 and 3. So this function we defined piecewise is just 2 whenever x is less than, let's call that 2 because I like the number 2. S is less than or equal to 2, or 3 when x is greater than 2. Just like anywhere here, it's 3. Anywhere here, it's 2. But right here, there's kind of this big jump. It's a hole. We don't like it. It doesn't look continuous. Is it connected? No. Is this connected? No. There's also another continuity, which I should have prepped better for, because I just did this all. But it's called an asymptote. If this sort of thing happens, which is like this goes up to infinity, it's not continuous right here because it's this kind of weird infinite hole thing. But maybe at infinity it connects. Maybe it's continuous. I don't know. We should have some way of defining it. But first, let's test our intuition. Is this continuous? This thing, not this, that I accidentally erased that. Is this continuous? Let's zoom in. Oh, look, it's continuous. It's connected. Whew, we're done. Let's move on. Wait. Let's double check. Let's zoom in a bit. Resize. Let's zoom in. Still connected. But our wires are very thick, so let's see if this is still actually true. Uh-oh. Uh-oh. There's actually a jump. We zoomed in enough and there's a jump. Oh boy. Do we have to zoom in infinitely far if there's a very small little jump? What if this jump was even smaller? We'd have to zoom in even further. And that would be annoying. So, what is continuous? Well, the intuition we have, it's connected, that there are no jumps. Okay? So, simple functions like this, where just f of x equals x, that's continuous. What about sine of x? That's continuous. What about whatever that is? That's continuous. What about this? That's continuous. What about that? That's continuous. All of these things are continuous. Note that there's something special about like points like this, which are called cusps, which is like changes direction so quickly. That doesn't affect continuity, so we're not going to talk about it at all. That's a differentiability thing. So if you want to talk about derivatives, and I know how happy you guys are about derivatives, yeah, no, we'll stick with continuity. Like all of these things are continuous. How do we define continuity? Well, first, we actually have to look at something called a limit. The limit of a function. It's a very simple definition. So, well, first mathematically, we say the limit of f of x is equal to L. When x goes to x naught. At a specific point, it equals L. So if we were to draw this, it would look like, boop, this is our x naught. Let's say this is our L. The limit is basically saying like that. That's basically what it's saying, okay? There could actually be a hole here. That's why I say L and not f of x naught, because this might not be defined. The limit's defined. Here, the limit is defined, but the function isn't. That'll come into play later. It's actually a very simple definition, this is. It's called the epsilon delta definition. It's okay, so give me an epsilon. Give me an epsilon greater than 0. This is like a width. It's how far away we are from L. Then there exists a delta greater than 0 such that if x minus x naught is less than delta, that's just how far away from x naught. Sweet, yeah. Then f of x minus L is less than epsilon. Boom, done. Easy. Okay, sweet. I'm done. See you tomorrow. Wait, what is this actually saying? Okay, let's clean this up a bit. Let's show you explicitly the different steps. There's 4 steps here. There's 4 parts to it. Oops. Okay. Give me an epsilon greater than 0. So let's make this a bit clearer. Okay, let's zoom in. I'm gonna make myself a big function. Okay, I'm gonna make it arbitrary. I'm gonna go like that. Okay, this right here is our x naught. Okay, and so let's guess that this is our L. Okay, then what we're saying is, given epsilon greater than 0. So let's start with the first step. Give me an epsilon greater than 0. This is arbitrary. Okay, but just give me an epsilon greater than 0. This is our epsilon. It's this width. So this is L minus epsilon. This is L plus epsilon right there. And what you do is this gives you a vertical region in which we need our function to be nice in. And what do we mean by nice? Well, there exists a delta greater than 0, such that if x minus x naught is less than delta, let's do both of these at the same time, because x minus x naught is less than delta. So delta has to be on this x-axis. This is our delta. Droop. That's our delta, okay? And then, if x is in this region, okay? If x is here, then our function minus L is less than epsilon. Basically, this is creating a horizontal, this is creating a vertical. What we're saying is, if x is in the horizontal, then f of x is in the vertical. Or we can create a box. And if our function is always within this box, we're good. It's done. But that's just for specific epsilon. What if the epsilon, boop, were this? Then, does our delta work? Look at our delta. It's in this region and this region. So it's boop. Is our x here always within? No, it's right there. There's a problem. That's a problem. That's out of the region. Oh no, it's not Wait, there exists. It's not for all delta. We can create any delta we want such that this is true. What if we were to make our delta smaller? Whoop, that's not how I want to make it. What if we were to just make our delta smaller? Right there. So now, this is our delta. And this is our epsilon. So let's look at this box. Are we always in this box? No, actually, you actually got to make it smaller. Boop, right there. Now, let's look at this box. Are we always in this box? Yeah, sweet. Okay, what if someone would pick a really small epsilon? And our delta still doesn't work, but we can create a smaller delta. Yeah, smaller delta, yeah, boop. And now it works. And we can just keep going, create this smaller and smaller box. And if we're always in this box, then the limit exists and is L. So let's do a simple example of this to like really cement this idea of creating boxes. We have a simple function f of x equals 2x. First, we could just look at it and be like, yeah, there's no place where we have 0 divided by 0. It's just going to be nice and continuous. But why? How? How do we know that? Give me an epsilon. 10, 6, Let's just say it's an epsilon. It's arbitrary, so let's just call it epsilon. Okay, let delta equal, because we want to just exist. So we can create whatever delta we want. So we're defining delta equal to something, but I don't know what it is yet. It's kind of hard to tell sometimes. But what's the next step? Next step is if x minus x naught is less than delta. So if x minus x naught is less than delta. Okay, ooh, look at this, look at this. First, give me an epsilon. This is our L. We're saying L is 4, okay? We're testing L equal 4. Okay, well, our epsilon, boop, epsilon, boop, epsilon. So this is our vertical region. Okay, we want to be within this region. Okay, let's see. What do we want our delta to be? Well, if x minus x naught is less than delta, then, this is step 4, f of x minus L is less than epsilon. F of x minus L is less than epsilon. Well, how do we know this? Do we know that? No, we don't know this. We need to prove this. So we can't actually say that yet. But f of x minus L, well, what is that equal to? Let's use our definition of f of x. Is equal to 2x minus our L is 4. 2x minus 4. Our x naught here is 2. So x minus 2 is less than delta. Okay? Because we defined x not equal to. Okay, well, what about this? Well, from algebra, we can just actually pull out the 2 from the absolute value. And now, well, we've seen this before, haven't we? Yes, we have. It's right there. It's defined to be less than delta because, that's just what we do. We just say we're in this region. Okay? This is our delta. We're just in that region. So if we're in this region, this is less than delta. So we can just say that this is less than 2 delta. Now, delta can be anything. We have yet to define it. We want this to be less than epsilon. So what if that is equal to epsilon? In which case, delta is equal to epsilon on 2. So if delta is epsilon on 2, so delta has to be much smaller than epsilon, by half in this case. We can create a box around it such that if epsilon over doop, boop, we are within the box, and that is nice. Look at that. We're within the box. There's no points outside of it. This is a simple case. There's some more complicated cases. Can you tell me what the delta is for a given epsilon in this function? No. Good luck. But it is technically possible whenever it's continuous. Wait, continuous. What is that then? Continuity is very simple, okay? F of x is continuous at x naught. This is going to be important. It's a very minute detail, but I'll mention it. So f of x is continuous at x naught if the limit as x approaches x naught of f of x is equal to f of x naught. Isn't that what we had here? No, but here, see, we had is equal to L. This might be undefined. Remember this, x minus 2 over x minus 2? It doesn't exist at x equals 2. But the limit does, because the limit would be the same 1, but it doesn't exist there. So the limit isn't quite as powerful as continuity. But if the limit exists, and it is equal to f of x naught, then it is continuous at x naught. So in the case of a whole, the limit exists. The limit is there from both sides. But the actual value doesn't exist, which means it can never be continuous. In the case of a jump discontinuity, the limit from this side exists, and the limit from this side exists, but they're not equal, which means the limit as x approaches x naught, because this can be from any direction, doesn't exist. It's not equal. It's not nice. So it's not continuous. For the real functions, it's easy to show this. All you need to do is as x approaches from the left side and from the right side. If you're in the complex plane, which is what my professor was talking about, then you actually can approach it from any direction or spiral in, or it's a little harder. But all we're saying is if x is continuous, then the limit exists and is equal to that point. A case where the limit exists and the point exists is here. The limit from this side is equal to the limit from this side, but the point is up here. Yeah, it's not continuous at x naught. Now, how do we know if f of x is just a continuous function? Well, it's just a generalization. if f of x is continuous at all x naught, at every single x, f of x is continuous in this way, then f of x is just fully continuous everywhere. And how do you do that? You generalize. What if instead of saying L here, we just said f of x naught? Okay, if it's well defined, if we can define f of x, like this is undefined, we can easily figure that out from the divide by zero error. But if it's well defined everywhere, if there's never a point where it's undefined, okay, this is well defined. But then we have to take the limits and we see if they equal that. Who knows what it is, but it's fine. Oh, that's all of that. So basically, what is continuity? Continuity is, are things smooth, continuous, and are there any gaps, holes, weird jumps, boop, boop, who knows? A function is continuous if we can create a box. Actually, let's look at this one. If we can create a box such that if within this box, the function is always within that box, okay? Where the vertical side of the box can be anything, and the horizontal side of the box depends on the vertical side. So we can make the horizontal side as small as we want, but the vertical side has to be at any vertical, we can create a horizontal such that it works. At any vertical, we can create a horizontal such that it works, okay? It's not the same as at any horizontal, we can create a vertical that works. Actually, that might be equivalent. Interesting mathematical endeavor to look at that. But it's the epsilon delta. Give me a vertical region you want it to be in. I will give you a horizontal region to be in. And this, if we're in the horizontal region, then we're in the vertical region. Then we're in this box. And this is what defines continuity. If our function is outside of this box, if our function goes up there, it's not continuous. It's not continuous. So when we have all of these, it's all of these things, well, let's look at this point. That point, okay, the vertical region is right there, so the horizontal region is right there. Boom, done. This thing, oh, right there. Boom, a vertical region right there, a horizontal region right there. Boom, done, we easy. This part, ooh, vertical region right there. Horizontal, actually our function's never in this vertical region, in which case it's not defined. It's not continuous because it's not in this vertical region. No matter what, and let's zoom out a bit, make it a little clearer. No matter what delta we have, if this is R, actually, let's say the limit is supposed to be here. If this is our region, okay, and this is our x naught, so that's our epsilon. No matter how small delta is, on the left side, we're fine. But on the right side, we're outside of the region. No matter how small we make it, if we zoom it in, there's still that little bit up here that's outside. So this isn't continuous because we're never within this box. In these cases, same thing. There's always a box that's missing, or maybe it's undefined here. If it's undefined here, then the limit doesn't, because we have f of x doesn't exist. In this case, we were doing the whole limit thing. It's not continuous. Like, you can look at a graph and easily see it, but is it always easy? Because what if we zoom in and then there's actually another hole right there? Who knows? Well, I know, because I can prove it. So, have a great day. I will see you next week. And I hope that this understanding of continuity, this idea of boxes, is at least somewhat helpful.